here and speak today. And I will, as Galen just introduced me, well, kind of my core interest over these years.
A little louder.
Yeah. Oh, let me see if I can turn on this stuff. Is it on? Or okay. Then okay, I'll try to speak louder. And my interests over.
I have
okay.
another microphone that'll actually go on here if you want.
Oh, is it okay?
This is only for the camera.
Okay, I'll try to speak louder. Okay, my interests and now interests of the group I'm working with at the University of Chicago revolve around wet chemical synthesis, a colloidal synthesis, solution phase colloidal synthesis of inorganic nanostructures. And over the last 15 years, the field developed into pretty powerful branch of synthetic chemistry where we can take many technologically important materials, technologically important semiconductors, metals, magnetic materials, and make them in form of crystals, with tiny crystals built out of few thousand atoms each, and control their size, shape, or chemical structure, chemical composition. For example, we can make multi-component structure in form of dumbbells or core shells, or we can make branched structures, wires, and all. It's a typical. It's a solution phase chemistry. So our wet chemistry labs look like ordinary chemical synthetic labs, and these materials are made in solution and in well, that's how they look in transmission electron microscope. So they are typical nanocrystal is something like 10, 20 atoms across. But if you will look kind of at a more detailed structure, it will always have crystalline solid core, and it will be surrounded with a shell of ligands or surfactants that we must put at the surface of the nanocrystals during the synthesis. Those ligands, they play crucially important job in defining particle size and shape and driving synthesis towards controllable formation of target materials. And please, yeah, I want to point your attention, stress your attention to these ligands, because they will be an important part of discussion, our first discussion today. And the field is getting mature now. 10 years ago, when I made my first synthesis of nanoparticles, we could make controllably only cadmium selenide. And over the years, work of huge community of people around the world led to numerous recipes, development of recipes for almost any technologically important 2,6, 3,5, 4,6 elemental semiconductors. And same is happening at the side of metals and plasmonic materials, magnetic materials. So it's now we have a huge selection, or large selection of material, of building blocks, pretty controllable building blocks with tailorable electronic properties, magnetic properties to start just design materials out of them. I don't want to say that the synthetic methodology business is over. For example, still nobody was able to make any reasonable quality gallium arsenide colloidal nanomaterials. But we now have good selection. At the same time, I want to point out that, well, if you ever want to use these materials, use colloidal nanomaterials as building blocks of functional devices such as light emitting devices, solar cells, thermoelectric heat converters, you will deal not with individual particle, but with array of particles or ensemble of particles. And it will be very important not only to understand electronics, electronic properties, photophysics, and electronic structure of individual dots, but you will also have to understand and how particles talk to each other, how carriers can be injected into particles from the outside world, extracted from the arrays, and interparticle communications, collective interactions. That's a significant part of our research. But even before you step into it, you should learn what happens when particles are approaching each other, how they interact with each other, how they pack into some macroscopic structures. And well, it's first, if you are good at synthesis and you can make uniform particles and then disperse them in a colloidal solution, well, if you, when you will let carrier solvent to evaporate, the solution will concentrate and particles will eventually emerge as ordered solids, ordered arrays. And there is nothing unique actually at this. Same would happen at different length scales with larger particles, for example, or even metal beads. The reason is that the system tries to increase packing density, or pack objects as densely as possible. And for single particle, for single type of particles, it will be usually a face-centered cubic lattice. And over the years, we learned how to grow two-dimensional arrays out of different structures, and it's pretty easy. We can, with some effort, you can grow three-dimensional array crystals. So this is a crystal of nanocrystals, where each individual particle is a tiny ferromagnet. And or you can grow three-dimensional arrays of semiconducting particles, where each particle is a tiny quantum well, and it's their zero-dimensional quantum well, and they are arranged into long-range ordered three-dimensional assembly. It's an interesting class of materials, and it's well, first it's kind of a new type of condensed matter, where you have several degrees of hierarchical arrangements. But and also we also use it as a very convenient test bed for studying fundamental aspects of crystallography, crystal growth. For example, it took us years to understand what these little grooves means, dimples mean. It's re-entry grooves. It turned out to be re-entry planes around twinning planes, and well, you can do many interesting things there. But you can make a next step, and that's turned out to be even more interesting, where you you independently prepare two types of nanoparticles. For example, you cook cat selenide nanocrystals and independently make gold nanoparticles. Mix two colloidal solutions together and let solvent to evaporate. And if you hit the right spot in the parametric space, or just control temperature, pressure, and solvent, then this solution, upon evaporation, will undergo disorder to order phase transition, and the particles will peg themselves into pretty sophisticated two-dimensional arrays, and three-dimensional arrays of binary. Like, for example, in this structure that was self-assembled out of solution, the gray spots correspond to lead selenide nanocrystals, and the dark spots are gold nanoparticles. We usually study these structures by transmission electron microscopy in real space. And that's a big advantage of these materials, because you can really study crystal structures or with single particle precision in real space very easily. And in many cases, for example, this particular structure is isostructural with copper-gold intermetallic compound. So this is a type of unit cell that you can find by looking at the doing transmission electron microscopy along different zone axes of the crystal structure, so using tilting experiments. And we name these structures following their unit cell type. So and well, our contribution to the field was that some years ago we found enormous structural diversity in what can self-assemble, spontaneously self-assemble out of fully disordered solution, just containing only two types, a mixture of two types of spherical particles. And as you can see, like we can have many different unit cell types. For example, this picture shows 12 different spontaneously assembled structures, and there are 3 polymers for where you have one small particle per one large particle. Or you can make 3 different polymers where you have 2 small particles per one large particle. And again, they are named after their unit cells. So it's not a chemical composition, it's more like a type of ordering of spheres. You can make AB3 types, AB4, AB5, AB6, and many more, even more sophisticated structures. well, this observation somehow defied traditional expectations and prior theoretical works in the field of sphere packing, because the belief was, or the kind of theoretical, the outcome of theoretical calculations was that if particles were hard spheres, then only 3 binary structures should be stable against phase separation, thermodynamically stable about phase separation. And it's definitely not happening. So for us, the big challenge is to understand with a reasonable level of detailization what's happening, what is this magic force that brings 2 particles and pegs 2 types of particles and pegs them into very complex arrangements. Well, from some very general perspectives, of course, particles do interact. It was not appreciated in the early days, but now these are zoo of observation, zoo of structures spontaneously formed that clearly shows that particles talk to each other and they feel interparticle potentials. And some of these interactions are such as van der Waals or electrostatic interactions. They are unidirectional, and some of them also particles. Almost every semiconductor particle has certain dipole moment, and you have dipole-dipole coupling, charge-dipole coupling, and these interactions are directional, and all of them contribute to the interparticle potentials. Okay, so the simple, what people do in theoretical studies, they usually develop interparticle potentials, then put them, and then use them to calculate phase diagrams. And well, actually, it turns out to be much more challenging to do it in case of binary superlattices, into nanoparticle superlattices, rather compared to molecular or atomic compounds, because there is a general theme propagating through the entire molecular or atomic world. In terms of, you can find charts or tables in almost every classical physical chemistry textbook showing what is the typical magnitude of the, for example, Coulombic interactions or charge dipole interactions in atomic and molecular substances. And of course, the absolute numbers depend on particular molecules or ions involved. But the general pattern is very general. So you always have the strongest, these interactions are spread over 3 or 4 orders of magnitude and are almost equidistant, nearly equidistant on the in the logarithmic scale. So the idea is that you always have the hardest player, the strongest player in the system. If for example, you're in sodium chloride crystal, absolute majority of properties is determined by Coulombic interactions, by modular energy. And all other interactions, such as van der Waals, they play a very minor role. And same actually applies to macroscopic world. You will have slightly different type of interactions. For example, you will have gravity on top, but it's still relatively simple. You usually have 1 or 2 dominant players. And it turned out that for the objects in the size range from few nanometers up to a few tenths of nanometers, all these interactions squeeze into same order of magnitude. I don't know exactly if it is if there is any deep physics behind it, or it's just a coincidence for these particular particles. But from practical point of view, we have multiple interactions. Each of them has a different scaling law, and they all contribute with comparable weights to the interparticle potential. So the optimistic vision of it, we can plug extreme, very high level of complexity and flexibility into the interparticle interactions. At the same time, of course, the question is how pure can be phases, if we can achieve high phase purities and other things. And but that's only one part of the picture. In addition to enthalpic interactions or just interparticle interactions, you have also entropy that contributes to the free energy. And the entropy, entropic contribution during self-assembly of particles can be rationalized on the basis of non-interacting particles in the box, and their entropy will be the entropy of this system will be dominated by translational and rotational degrees of freedom for each particle. And essentially, it will be related to the volume per particle. free volume per particle to move. And it turns out, and when you start evaporate solution, so you can compress this box and particles start just bumping into each other. So, and actually, it's when in case of one type of particles, once they approach, occupy about 50% of available space, then you will end up with disorder to order phase transition, because in ordered state, particles can it's kind of counterintuitive. You order particles in form of colloidal crystal, but at the same time, the volume per particle to move locally moved becomes larger, and the system gains entropy. And well, okay, so now the question is, very fundamental question is, what is more important, enthalpy or local interactions or entropic interactions? And we had no clue what's more important. So we decided to use temperature as a weighting factor between enthalpy, between internal energy related contributions and entropic contributions. There was a whole bunch of technical issues with these measurements, but actually we looked at, we've been able to work most of them out. And now the simple experiment. You mix two types of particles. You like almost nearly 8 nanometer lead sulfide, something like 5 nanometer palladium. And you have exactly same particle size ratio. The only different parameters that you change in this system is temperature. And we observed very reproducible phase transitions driven by temperature. And so to make, from practical point of view, it's a very nice way to change phase diagram, to move through phase diagram. From a kind of more general perspective, it's it shows that in this equation, entropy has nearly same weight to the free energy as interparticle internal energy related interaction. So we have very complex system, and the only way for us to move through this complexity was to learn or develop some nearly empirical rules how to cancel as many interactions as possible. And one of the examples here is that we found how to treat particle surface in order to end up with electrically neutral particles. So it really minimizes interparticle potentials. Then then free energy will be determined by entropy. Okay, now we have we can have same particles taken into two different packing lattices. One lattice is isostructural with aluminum boride, and 001 projection of this lattice, we can describe it as triangular packing. And on the other side, we can pack same particles into superlattice isostructural with calcium hexaborate. It's a pretty remarkable structure because you have simple cubic arrangement of large particles, and in the center of each cube you have a small octahedron of 6 small particles. So, don't ask me how this assembles, how it was possible to spontaneously assemble such a complex structure, but it forms. Now, and they can form under very similar conditions. What we can do next is to try to match translational and rotational entropies associated with self-assembly process for both structures, and to do this, in a hard sphere packing or in sphere packing theories, there is a clear connection between entropy during self-assembly and the packing density, space filling of the structure. The more dense structure, the more dense your assembly is, the higher will be entropy gain during crystallization process. Okay, with nanoparticles, we can very precisely tune sizes of both components. And we can, so for each of these lattices, we have space filling factor, space filling curve. That is pretty directly plugs into translational entropy during self-assembly process. And then now we can tune particle sizes, the ratio of particle sizes, in such a way that these two curves cross. They cross at a gamma ratio of 0.43. So now we minimized internal energy during associated with self-assembly process. We minimized entropic contribution. So the system should decide which structure to adopt based on some different principles. And this principle will be related to stoichiometry of the system, to the stoichiometry or ratio, particle number ratio, large and small. When we have a deficit of small particles, we will adopt these structures, AB2 structure. When we use large excess of small particles, B particles, gold particles, we will adopt this AB6 structure. Now, what if we explore phase diagram in between? In that case, we found that we form self-assemble superlattices that have both square and triangular motifs. And they might look messy and pretty complex, but actually diffraction patterns show, electron diffraction patterns show that they are perfectly long-range ordered. We have some more complex structures combining squares and triangles. And it took us years to understand what's going on in this system, what type of packing motif we end up with. And it turned out that these particles self-assemble into structures known as, or this structure can be mapped on something known as Archimedean tiling. And Archimedean tiling, it's a tiling pattern. And what is special about this pattern is that every type of vertex is identical. For example, in this lattice, or in this mapping, we can pick any vertex and it will be triangle, and around it we will have triangle, 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 so 6 triangles. In this structure, we can pick any vertex and it will be surrounded by triangle, triangle, square, triangle, square. We can pick, for example, this vertex, and again it will be triangle, triangle, square, triangle, square. And there are only 4 Archimedean tilings that can be made out of squares and triangles, and only 11 of them can be made on plane. And others are pretty not physical, so they require very sophisticated tiles. But so after we learned that we can make that such structures can form through self-assembly, and I also came across earlier theoretical works that actually these structures can coexist, or Archimedean tilings often coexist with something much more weird. And this is, again, it's no chemistry, no physics, just squares and triangles, and their tile. And if I will ask you about if these structures have any type of translational symmetry, or if it is periodic or not, well, it's not periodic. It has no repeating units. But this, what we have, this is Fourier transform of infinitely large domain. So in terms of crystallography, it's a perfect long-range ordered system. It's single crystal type pattern. But the structure has no translational symmetry. And another weird thing about this structure, by counting these spots, you can say what is the rotational order, what is the symmetry element, what is you can assign to this structure. And it will give you 12, you will have 12 spots. So this structure nominally has, this lattice has 12-fold rotation. And in classical crystallography, it's equally forbidden as 5-fold rotation in a crystal. So it cannot, these two things cannot coexist. And so now we have long-range ordered structure, we have forbidden symmetry element, and we have no translational symmetry. And all this can be plugged into the nanoparticles. So that's how we made first structures, and and this is actually, this is self-assembled nanoparticle superlattice, and this is electron diffraction pattern, which with 12-fold rotation symmetry, and this is the structural, this is the stoichiometry, so it's a rational stoichiometry. Kind of a bit weird. And how we derive this stoichiometry and how we compare this with experiment, from theory, from theoretical studies, we knew that the main, this structure can be built if or forms when your total area under squares is equal to the total area under triangles. That's what will give you irrationality. And also, the second requirement to build this fancy structure, you can swap tiles until you approach maximum of entropy. It's the most possible. It's the most disordered tiling under conditions of equal areas. So, and that's what probably drives self-assembly process. Once we cancelled out internal energy and or minimized internal energy contribution and cancelled out translational and rotational entropy contributions, then structure will adopt then configurational entropy of the lattice itself can play important role. And here in this structure, since it's highest entropy possible packing, the configurational entropy will be higher than any periodic lattice. Okay, that was kind of a first demonstration of nanoparticle quasicrystals. And then we've been, they kind of built can be rationalized as an arrangement of squares and triangles. First nice thing about it, thing to be proud about was that prior theoretical works totally overlooked this type of packing. And the second important thing was that we found that the key to form these structures was really particle size ratio. Once we made other materials with this size ratio, you can self-assemble them. For example, this structure is assembled of iron oxide and gold. You can self-assemble of lead sulfide and palladium, or you can use different phase of iron oxide in different size and another gold. And they've been reproduced in Chicago. They've been reproduced at UPenn. And so it's but of course the question was how can we contribute to the field in general? How can we contribute to the understanding of quasicrystals or aperiodic lattices? And this is example of probably the best or most fascinating crystal or structure grown from with this nominal composition. It's a ternary intermetallic compound, and this is in terms of crystallography, it's a single crystal with 5-fold symmetry elements. And this is this quasicrystal was grown at Ames Labs, and this is the composition. So that's kind of similar concept that materials that or structures that have no translational symmetry, have forbidden symmetry elements, but form perfect long-range order. But the question in the field, and this field, like the first discovery of quasicrystals in aperiodic structures in intermetallic compound was made in 1984. So for about 25 years, there was a very important puzzle in the question. What is the role of directional interactions in this? Because we have holmium, we have d orbitals, we have f orbitals, they form a complex network of interactions. So the question is, what are the magic forces that assemble such complex aperiodic structures? And we've shown that you don't need any magic forces. Just a packing or entropic principles or sphere packing principles can, like derived by particle size ratios, can be sufficient. I don't want to say that they are always dominant, but they can be sufficient to self-assemble particles into quasi-periodic patterns. The other important questions that we've been able to address in that work was that, now we have kind of two worlds. One world of conventional crystals, periodic structures, and the world of these weird animals that are aperiodic. And they are built upon completely different topological principles. Now the question is, or was, and still of course is, how these two worlds can interface each other. If it is possible to make a connection or interface, how the interface between a crystal and quasicrystal should look like. If it is possible to make something like epitaxial relationship between crystal and quasicrystal. And it was for atomic systems, it was very difficult or nearly hopeless to study, because you need to you need to map large areas with atomic resolution and unambiguous atomic resolution. But with nanoparticles, it was a very simple experiment. well, we had many domains, quasicrystalline domains, and all we had to do is to look what is at the edge of this domain, how it interfaces to our outside world. And we collected pretty large statistics of what's going on at the interfaces, and we found that indeed quasicrystalline, dodecagonal quasicrystalline phase can pretty nicely match, for example, to calcium hexaboride phase. But the interface, the interfacial layer, the interface should be always have a thin wetting layer, and this thin wetting layer, in all structures we saw, was a thin few unit cells of this 3 cube 4 square Archimedean tiling, and so you need to form first quasicrystalline layer, then so-called pseudomorphous layer of Archimedean tiling, and then it can perfectly match to the crystal. Okay, that was kind of introduction to our work on assembly process, and we hope second part of our project of our research program is related to transport, to understanding how particles in such superlattices can communicate, can talk to each other, and that's a very important point for us and for community in general, because, well, understanding of interparticle electronic interactions, electronic coupling between particles is a crucial key step to development of any practical applications or to using the particles in properly designed and engineered colloidal nanostructures in photovoltaics, in thermoelectrics, in light emitting in photo detectors, in any application essentially. And so everywhere where we hope to replace single crystals with nanogranular materials, we should understand the communication between the individual grains. And from very simple and mechanistic point of view, if you have, for example, array of nanocrystals, and so where each particle is, for example, really nice piece of semiconductor, but is surrounded with a shell of ligands, then the charge transport in such array will depend on several parameters. First, usually, your transport will be through localized states. Your particle will go from, or your electron will go from one particle to the other, and they will, and the energy levels in different particles should be relatively matched to each other. That's matching site energy. Second important parameter to look at is the exchange coupling energy. Exchange coupling energy is, well, the wave functions of individual particles should overlap to enable transport. And the third parameter, but even if these two parameters, these two requirements are fulfilled, then you still can have many problems with transport. And that has been theoretically and experimentally studied over the last many decades in disordered conductors, in amorphous silicon, in the field of theoretical physics called granular electronic systems. Well, the problem is that, for example, if you have a granular system, it's just energetically costly to put a charge on a conducting sphere, to localize charge. And this will lead to electrostatic charging energy that is inversely proportional to the size of the particle. So when particle size goes down, then charging energy goes up, and you open what is called Hubbard gap. And so the material that can be, that appears to be a good conductor, in reality can end up to be a Mott insulator for it. And there are Anderson localization and a whole bunch of other problems. And so from a chemist's perspective, it shifts slightly focus from properties of the particles themselves to the interfaces, to the communication to these areas that we don't see here, and to this role of surface ligands, or what is around the coating of on the particles. And each layer of coating forms a tunneling barrier, and it leads to localization of wave functions on individual particles. And well, if we don't do right job as chemists, we will end up with just insulating layers where particles, for example, we can bring together a semiconductor and magnet, and they will not couple to each other. So, and that's what happens when you use ligands or surface ligands that are necessary for colloidal synthesis. So just array of colloidal particles or film of colloidal particles is very poor conductor. And some years ago we found a nice trick how to make particles, how to improve conductivity in a very simple fashion by 10 to 11 orders of magnitude. So we found that we can replace these bulky ligands with a small molecule hydrazine, with hydrazine molecules using dilute solutions of hydrazine in acetonitrile, and that increases conductivity very quickly and by orders of magnitude. And that's how we just started with colloidal solutions, treated them with 1 molar solution of hydrazine in acetonitrile, and converted pretty good insulator into the first field effect transistor made out of nanoparticles. Now so the mobility that we observed in nanoparticle layers was on the order of 1 centimeter square per volt second, what's pretty comparable to what you can get out of best organic electronic materials. And another useful advantage of making nanoparticle transistors was that we can use these transistors as a tool to study electronics, charge transport, to study trap states and other things. For example, if you make a transistor, is you have a layer of particles, you have 2 electrodes, source and drain electron, and then you have a gate, third electrode, that is capacitively coupled through a layer of insulator to the nanoparticle array. And then when you apply voltage to the gate, you can change the doping or concentration of mobile carriers in the nanoparticle layer, and then you can turn it on and off, or you can increase or decrease conductivity of this layer. That's essentially how field effect transistor operates. And from the slope of this curve, you can immediately extract what is called field effect mobility, or mobility of carriers in the film. And well, again, we can measure it for many different materials. We can look how it depends on particle size, and there are many different effects involved, many interesting physics involved in this transport in structures where you have very good control over granularity and other things. For example, we clearly see that we have optimal size for mobility. It goes down on both ends, and so in arrays, in FCC arrays of nanocrystals, well, the optimal size is about 8 nanometers, and it applies to many systems. We don't quite understand what is the physics behind it yet, but yeah, but we can, as a chemist, we can try on some more interesting things or more weird things, because well, just array of, for example, lead sulfide particles it's a very neat example of just nanogranular electronic material. And in principle, it can be described, and it is well described by existing theoretical frameworks. Now, what would you say about? Well, but now we can use the full power of colloidal chemistry, or ability to grow complex structures, multi-component heterostructured phases, and combine it with transport ideas. So, for example, we can make what we made some years ago. We made tiny gold particles and encapsulated it in semiconductor. Now, these two, metal and semiconductor systems, are in the regime of very strong quantum mechanical coupling, just because the physical size of the wave function in lead sulfide is larger than size of this particle. So these two components are very strongly coupled to each other. So for us, the first question was if it will behave more like a metal or more like a semiconductor, what to expect. And it turned out that actually the arrays of these particles, of these heterostructures, behave more like, they behave like semiconductors. So we can modulate current through them. But another quite interesting observation for us that lead sulfide particles, under our conditions, they always end up n-type semiconductor. And these arrays of gold lead sulfide heterostructures always show very strong p-type, nearly close to degeneratively degeneration level of p-type doping. So further studies have shown that we form kind of interesting we enter quite interesting situation where we form intraparticle charge transfer complex. So the highest state in the gold is lower than the highest highest occupied state in semiconductor shell. So you have charge transfer from the shell into the core, and you end up with mobile holes. So people observe charge transfer complexes in intermetallic compounds, in some organic electronic systems, but yeah, they've never observed something like this in colloidal or in nanostructure, inorganic nanostructures, at least to the best of my knowledge. And well, then we made another interesting system. We made what we called magnet in the semiconductor nanostructures. So this, each of these particles has a tiny piece of ferromagnet called iron platinum, integrated into a single crystal, tiny single crystal of a semiconductor, lead sulfide, or lead selenide in this case. Then again, for us, next question was the important question: how these structures would behave in terms of transport and magnetic properties. And it turned out that actually, well, we do not harm each of these functionalities. This array of particles will behave more like it will be superparamagnetic at room temperature and will be ferromagnetic at low temperature. And at the same time, we can control currents. We can control currents through these arrays by using electric field. So we can make transistors out of them and can get pretty decent field effect mobilities in such arrays. So it's kind of both magnetic and semiconducting system at the same time. Well, the question for us was the next, of course, question to ask is the coupling between two subsystems. So if they talk to each other, like magnetic functionality and semiconducting, magnet and semiconductor. And we measured low temperature magnetotransport, and we found that we have many signatures that well, first we found that magnetic field can strongly affect transport or conductivity through these arrays of what we call magnet in the semiconductor nanostructures. And it looks like the mechanism of how it affects is determined by so-called spin-dependent tunneling. The idea is we have this particle, and the tunneling rate is proportional to, is dependent on the orientation of spins of electrons before tunneling and after tunneling. And so it means that it can be understood, well, in classical spin-dependent tunneling or tunneling magnetic or GMR heads, giant magnetic resistance heads or magnetic tunneling junctions. It is described by the difference in the density of electronic states at the Fermi level for spin out and spin down configurations. So, and well, first, and that's kind of striking because, well, we have tunneling probably from here to here, from lead selenide to lead selenide. Lead selenide doesn't, or lead sulfide doesn't have any difference in the doesn't have any spin polarization. So it looks like, well, we have very fast exchange. Well, we can speculate that we have fast exchange of carriers between magnetic core and semiconducting shell that introduces spin polarization into non-magnetic semiconductor. And well, so it's these examples show kind of what we can do and how we can use the power of synthetic methodology. And probably, of course, the field will develop further. We will make more and more complex structures, and hopefully we'll use them as electronic materials. But the bottom line for any, well, the weakest link and the bottleneck for any transport studies or for any attempts to apply these colloidal nanostructures as electronic materials will be limited by these interfaces. The interfaces will be limited by ligands. And traditionally, we and others used like large organic ligand molecules. Well, in the recent years, we first introduced hydrazines, and several groups after us used other small molecules. but as the interfaces. But it's, well, it definitely enabled many experiments to be done, but it's totally impractical. Hydrazine, molecular hydrazine is between particles, no way that it will survive 30 years in the field in a solar cell, for example. Same with small molecules. They are volatile, that are oxidizable, or dicyls. Well, so it's a general big problem. And in attempt to address this problem, we decided to redesign or rethink how the colloidal nanoparticle should look like. You can go to Wikipedia and look how people define colloidal nanoparticles. It is defined like inorganic core surrounded with a shell of organic ligands. And this, well, but we've been lucky to find a very good replacement for these organic ligands in general. And so we found that there is a very large family of inorganic compounds called, well, we call them molecular metal chalcogenide complexes. More, well, large part of this family can be described as zintal ions. But something like this can perfectly replace organic coating and make solution, colloidal solution of inorganic nanoparticles, and fully inorganic. So we have inorganic core, inorganic ligands, and and it's a very general chemistry. For example, we can make this tin sulfide metal chalcogenide complex and use it to cadmium selenide nanocrystals, to cat telluride nanocrystals, to nanorods, cat sulfide nanorods, cat selenide nanowires, essentially gold nanoparticles, many other things. Or you can also do a lot of work, rational work on design of these ions. For example, you can pick, start to use cat selenide nanoparticles and use design ions or these inorganic ligands based on tin or indium or gallium or copper or zinc or mercury, antimony, sulfide, chalcogenide, sulfide, selenide, tellurides, and with different structures, different motifs. And so it's kind of a very useful, very general methodology. Now, so they form perfectly stable colloidal solutions. In this case, we change type of colloidal stabilization from so-called spherical stabilization that is known for original well, that we have with in systems with organic ligands to just electrostatic stabilization. Electrostatic stabilization is provided by attaching charged species to individual nanoparticles, and they prevent aggregation. And as I already mentioned, it can be used with semiconductor nanoparticles, it can be used with semiconductor nanowires, and it even can solubilize or make stable colloidal solutions of large wires that would not be stable with original organic ligands. You can make use it with metal nanoparticles. You can even preserve ability of these structures to self-assemble. And very recently, like last week, we made binary superlattices using this approach. It can be used to some complex structures. Now, let me step back from nanoparticles and say what kind of strategies we use to make these ligands, to make these metal chalcogenide complexes. And a kind of, well, a starting point for us was the hydrazine-based ligands. And this chemistry was discovered by David Mitzi and published in 2004, and it's extremely simple. So the idea is that he used bulk metal chalcogenide, and hydrazine has, anhydrous liquid hydrazine has enormous solubilizing ability. It can dissolve like many metal chalcogenides in the same easy way how water would dissolve sugar. The only trick is you need to add some extra chalcogen, and then you will form stable solutions. So you can dissolve indium selenide, you can dissolve tin, for example, directly and form this tin sulfide. And this chemistry, you can make many semiconductors, even ferroelectric phases, phase change materials. using this technique. So we made this list of materials. Some of them have been published. Some of them you can find in follow-up papers by David Mitze. Some of them we just developed in-house. But so it's a very general and very simple trick. Well, again, but at the same time and we use it a lot for our experimental studies. But at the same time, I want to emphasize that for practical applications, hydrazine is not good, and it raises many scalability problems. So there is nothing special about hydrazine. We can do same chemistry using very simple, like aqueous type preparations. And we can make, for example, arsenic chalcogenides, tin chalcogenides without any hydrazine, and it works equally well. Now, another important point, of course. Every time when you put something at the nanoparticle surface, the question is what you do to electronics, to electronic structure. If you introduce mid-gap states, if you introduce charge trapping. And here it was pure luck for us that it found that these molecules do not harm electronic properties. We still have band gap, band edge, luminescence controlled by quantum confinement. We can form excitons, they do not quench, so we can make these bright samples. And in more recently we've shown that we can use it, we can combine this chemistry with viscose shells and make purely inorganic nanostructures without any organic ligands, with emission above 40% at room temperature. So we can kind of our next natural step would be to try to integrate them in light emitting devices, in other things that historically we're not developing fast enough, as far as I know, because of organics, because of these layers of organics and also problems that organics introduce at elevated temperatures. You can also use these ideas to design of near-infrared and mid-infrared emitting materials, because again, organics is not a big issue for luminescence or invisible, but in near-infrared and in mid-infrared, you have direct coupling of exciton to stretching modes of organic ligands that kills your luminescence, and here you can avoid many of these things. But generally, our work was motivated by transport. We wanted to make something conductive, and it's turned out that these ligands are much more electronically transparent compared to for organic hydrocarbon ligands. So we can if you have array of gold nanoparticles, you can put maybe even very short organic ligands, something like butane silyl. The conductivity that you have in these arrays, like 10 to minus 3 Siemens per centimeter. Probably the highest reported number is 10 to minus 2. And with these inorganic ligands, we easily get up to hundreds. And and this is a bit outdated. We have 800. We saw 800. So it means that we already are in the regime where we have collective. We should these to rationalize these high conductivities. You need to. You have to. We will come up to the conclusion that you form delocalized electronic states. And but then we can do even better job in terms of for designing transport materials. So the idea how I came across all this chemistry was again that very important work by Dave Mitze, who used these materials, exactly this material as a precursor for electronics grade semiconductor. So his way of thinking was that, this is quite unique material. This is quite unique molecules that do not contain a single carbon atom and do not contain any non-volatile residue that can be left behind, can contaminate your phase or your target phase. So that upon very mild heating, you will convert these materials into pretty good semiconducting layer with high electron mobility. And that's not easy to find such precursors for solution phase chemistry, because general problem is that you leave behind soot if you have a single carbon there. So it means that we can put these particles, these metal chalcogenide complexes at the nanocrystal surface, and then anneal them and convert, really glue particles together with a layer of semiconductor. Well, okay, it's easy to say, but the big question, of course, is if you can, if this chemistry or ligand exchange is as clean and as complete as we claim in our PowerPoint presentations. So, and to prove this, we did we used 3 different techniques. So FTIR shows that after ligand exchange, you have any residual CH traces. NMR and elemental analysis also shows that we for sure remove more than 99% of original ligands. So it's quite pure chemistry, and but still, so we have now very kind of inorganic structures where we still preserve all the benefits of quantum confinement or excitonic structure, tunability of the band gap, and both in solution and in films and even after annealed films. So the next thing for us, over last year, we learned how to make better transistors that we initially published in our that paper. So and we found that we can make array of particles, so with inorganic particles, spin cast a film, bake it a little at around 200 degrees or 150 degrees, and end up with, now I'm pretty confident that this is reproducible numbers. We can get mobilities, linear range mobilities, that are probably the hardest to get in disordered semiconductors, above 10 centimeters square per volt second. And we can combine that chemistry with, for example, co-shells, and get materials that have both high mobility and luminescence, band-edge luminescence. And can do many other things. One of the examples where we applied this methodology was development of or attempt to develop new thermoelectric materials. For example, you can make cat telluride nanocrystals or bismuth chalcogenide nanocrystals. Put at the surface cadmium telluride molecular species, cadmium or tin telluride based molecular metal chalcogenide complexes, form a stable colloidal solution, and use it as an ink either for drop casting, for spray coating, for pellet formation. And well, the numbers. So you get solution processed materials, and well, conductivities are in the range of several hundreds, about 300-400 Siemens per centimeter. Pretty good. Zibik coefficient state well, same that you would observe to fully optimized commercial bismuth antimony telluride samples. And again, following same solution phase chemistry, we can tune, for example, doping from N-type to P-type, and it's very simple. For example, in this case, we take a solution of selenium and hydrazine, and you add droplet of each to a formulation of your solution phase chemistry for bismuth antimony telluride. So you introduce selenium, and you change doping from P-type to N-type, preserving other characteristics. And well, so it's we did not beat any world records here. It's about ZT is close to 1 for these materials, at least based on our current measurements. And well, we did not do much optimization, but we really want one day to use this chemistry in a more thoughtful way to really plug the power of colloidal synthesis, or ability to introduce complexity or multifunctionality, multi-component nature into individual building blocks, and try to test systems that nobody was able to test in the past. So, and one of our rationings here, and one of our big hopes here, is that we can, well, by using arrays of nanoparticles, we can design the density of states and move out of from parabolic density of states known for any bulk semiconductor to something like more that has spikes, or ideally delta functional type density of states. And our preliminary measurements, well done that time, we did not have the inorganic ligands, so we used hydrazine approach, have shown that just these changes in the density of states will immediately gain you almost factor of 2 in the Zibik coefficient. And it gets size dependent, so you can do some interesting things along these lines. Do band gap engineering, or do electronic structure engineering. I don't want to say that it's a done deal, because especially at elevated temperatures, such structures should be very susceptible to sintering. Well, but there are many ideas that we can try using using synthetic methodologies that we have developed over last year. And at this point, I want to acknowledge really excellent team of people working with me at the University of Chicago and my collaborators at the Argonne National Lab, funding agencies that made all this works and possible. And of course, thank you for your kind attention.
We have time for questions, comments.
The approach we have taken recently is to eliminate the ligand altogether. We use butylamine, which functions as both as the solvent and as the ligand. And then with a mild temperature, you drive it away, and you get really a direct contact with the nanoparticles. And we demonstrate, it's not published, this is published in JAX, but photoconductivity of such systems, of such films, that we make that way pretty good. As good as almost as any conductor.
That's possible, but well, we did not have much luck with similar approaches. And well, the problem is, well, what we found that well, it's you can use kind of brute force to remove ligands, to strip off ligands. But the problem is that they will you have to do something with Dennin bonds, with under-coordinated surface sites that are present, always present at the nanoparticle surface. If you have nothing there, then you will generate high concentration of surface traps. So try to look at your transients, current, well, photoconductivity transients. You probably first should fill up all these like gaps, oh sorry, mid gap states, and only after that you have good photoconductivity. Well, at least I'm speaking only about my personal experience. Maybe you had better luck, but you need to have something at the surface. That
Your comment is correct. I mean, it's not a perfect single crystal. You have some state, but the states we found are very shallow. The steady state photoconductivity, transit is usually temperature independent, even in this order system. The peak transit photoconductivity. Steady state, in this case, is in the order of activation energy of 3 millielectrons. So it's pretty mild.
and what did you see in terms of dark conductivity?
Dark current is very good.
Oh no, dark current conductivity or carrier mobility in these structures.
The carrier mobility we did not measure directly, but what makes the photoconductivity so efficient in this system, it's cadmium selenide, is that you have long hole traps and you have a high photoconductive gain.
Oh, yeah.
So we have photoconductive gains that is in the 100 and 2,000. So it's very large. But the general approach, I want to emphasize, is that if you can, what we publish in JAX is that you can use a ligand that is very easy to drive away, and you have nucleation, and you heat it up, the film after the position, and you can make a good sintering and even melting because the size of the nanoparticle is very small.
You showed how when you increased or added hydrogen as a ligand, you increased their conductivity. It's not initially obviously why.
Okay. It turned out that hydrogen plays multiple roles in this case. So you have initially, well, to make good lead selenide nanocrystals, you have to use oleic acid as surfactant. Oleic acid is a carboxylic acid with C18 chain. So it's very bulky. Now, and it prevents you from any reasonable charge transport. When you use hydrogen, hydrogen is Lewis base. So it replaces oleic acid and from the surface. And we also found, and again it was quite lucky observation, that the film somehow relaxes without introducing cracks. So it just particles come closer together. That's not, it's just a first step. So you compact particles, you remove bulky ligands. Then you also, hydrazine it passivates surface Danelin bonds. It passivates surface Danelin bonds. It's also, it uses Lewis acidity. It's, it's good ligand, like coordination ligand. Then it's good reducing agent, because it turns out that for trap states, they are usually associated in this system with oxidized surface side. If you have a single oxidized surface side, it will repair it. And even in addition to that, well, as I already mentioned, the big hurdle in this entire game is dielectric mismatch. And so you have just the electric properties of the medium. And oleic acid has a dielectric constant 2, or about 2. Hydrazine molecules have dielectric constant about 52. And it very strongly reduces the electric mismatch between particles and media. So it reduces Hubbard gap.
No, now is a question. The way your ligand, the question is, do you pacify the surface trap with this ligand that you mentioned, the thin? Do you?
Yes. Yes, we see it. Well, the simplest way to probe it is to measure luminescence. Luminescence, if you see high luminescence quantum yield, it immediately says you that you don't have trapping at the time scales of tens of nanoseconds, and do not have trapping for both electrons and holes. So it's at these time scales we do not pursue.
Do they contribute to the dark current? These ligands?
In which regard? You mean doping, or?
Or just doping, or
they make film conductive. Let's put it this way. Depending on other factors, such as primarily heat treatment, you can tune the dop. The dark current in your system will depend on two parameters: carrier mobility and carrier concentration. So the ligands, and it's a product of both. And so carrier mobility is definitely enhanced by many orders of magnitude. Carrier concentration is a bit more difficult parameter. We describe it as a threshold for the threshold voltage for field effect transistor, and it's it depends. We found that it depends on the heat treatment and on the amount of the ligands we put at the surface. We can control it. So it can be either conductive, or you can have either high dark current or can have low dark current. That's how.
Okay, I think we'll thank Dmitri for a very exciting, interesting